Here's problem 1325. A 50 kilogram satellite circles the Earth in an orbit with a period of 120 minutes. What minimum energy is required to change the orbit to another circular orbit with a period of 180 minutes? Earth radius is 6.4 times 10 to the 6 meters. Mass is 6 times 10 to the 24 kilograms. All right, so we have Earth, and we have a satellite at some radius R1, which we don't know. And it goes around with a period, let's call it T1, of 120 minutes. So there's 60 seconds per minute. So let's get that. 7,200 seconds. All right, and then we want to change the orbit to a second orbit. Let's call it R2. And the period in that orbit is 180 minutes. Multiply that by 60 seconds per minute. And that gives us 10,800 seconds. All right, we know that the energy for any stable orbit, energy of binding, is going to be equal to negative g, mass of Earth, mass of the satellite, over 2 times its radius of its orbit. So that is the stable energy of a stable orbit, and that's what we're dealing with here. So in order to use this equation, we need to find out what R is for both our initial radius and our final radius. To do that, we'll use Kepler's third law. Kepler's third law says that the period squared is equal to 4 pi squared over g times the mass, central mass, times the radius cubed. So if I use this third law, let me put that 4 in there. If I use this third law to solve for the radius, then I would have that the radius is equal to g times mass times the period squared over 4 pi squared, all this to the cube root 1/3 power. All right, so my radius 1 is going to equal g 6.67 times 10 to the minus 11 times the mass of the Earth, which is 6 times 10 to the 24, over 4 pi squared, all that, times t squared, which is 7,200, and then all this to the cube root power. 6.67 times 10 minus 11 times 6 to the 24 divided by 4 divided by pi squared is 1.01 times 10 to the 13. Just want to use that. Keep that in mind. And then we have that times 7,200 squared, all this to the 1/3 power. I get 8.07 times 10 to the 6 meters. So that is my R1. My R2 is going to equal 1.01 times 10 to the 13 times t squared, all to the 1/3 power. So that is going to be 1.01 times 10 to the 13 times 10,800 squared, all that to the 1/3 power. And what does that give me? It gives me 1.056 times 10 to the 7 meters. Alright, so that's my second radius. Well, our change in energy is going to be our final energy minus our initial energy. That's the energy we need to change these orbits. So that's going to be equal to negative g, mass of the Earth, mass of the satellite, over 2 times R2 minus negative g, mass of the Earth, mass of the satellite, over 2 times R1. So this is going to be equal to g, mass of the Earth, mass of the satellite, over 2 times 1 over R1 minus 1 over R2. So this will be 6.67 times 10 minus 11. Mass of the Earth, 6 times 10 to the 24. Mass of the satellite, 50 kilograms. Over 2 times 1 over R1. R1 was 8.06 times 10 to the 6 minus 1 over R2, which is 1.056 times 10 to the 7. And we got to make sure we can put all this in without making a calculator error. I come up with 2.94 times 10 to the 8 joules. So that is the energy we need to switch from one orbit to the larger orbit. We need to add this much energy to the satellite in order to make the switch.